Today, let's talk about Chapter 5 Thinking, Planning, and Language. And from the moment you wake up, your brain is bombarded by stimuli. The sound of birds singing or the rumble of trucks, the smell of coffee, the brightness and warmth of sunlight streaming through your window. Fortunately, your brain is adept at filtering this flood of information and making a decision about what actions to take. Is it a workday or a weekend? What would taste good for breakfast? How warm or sweater do you need? Every moment you are conscious, you are thinking, planning, and making decisions. But how do you think? What is happening in our brains? And when we reflect on last night's party or puzzle over what to wear today, can other animals think the way that humans do? In order to think, your brain has to make sense of the noisy, chaotic world around you. The first filter for that information is your perception, which arises from the senses whose processing we considered in Chapter 2. The next step is interpreting those perceptions, which your brain does by comparing them to memories of past experience and observations. And first, we introduce the constructing representations. And because your brain's capacity to store this information in short-term memory is limited, it built fairly simple representations of people, places, objects, and events as references to really make sense of our moment-to-moment perceptions. The brain relies on its complex network of associations assembled from prior experience. These connections enable your brain to deal with variable perceptions. For example, you can identify a dog even if it is a different breed or color than any you have seen before. A bicycle still registers as a bicycle, even if it is obscured so that only one wheel is visible. And constructing these representations relies on semantic memory, a form of declarative knowledge that includes general facts and data. Scientists are just beginning to understand the natural and organization of cortical areas involved in semantic memory, but it appears that specific cortical networks are specialized for processing certain types of information. And studies using functional brain imaging have revealed regions of the cortex that selectively process different categories of information, such as animals, faces, tools, or words. Recording to the electrical activity of individual brain cells shows that specific single cells may fire when someone looks at photographs of a particular person, but remain quiet when viewing photographs of other people, animals, or objects. So-called concept cells work together in assemblies. For example, the cells encoding the concepts of needle, thread, sewing, and button may be interconnected. Such cells and their connections form the basis of our semantic memory. And then let's introduce scientific tools that many studies using a technique called functional magnetic resonance imaging, called fMRI, to measure brain activities in response to words have found more extensive activation in the left hemisphere compared to the right hemisphere. And however, when words are presented in a narrative or other context, they elicit fMRI activity on both sides of the brain. And then about language processing. As the picture says, As the picture shows, a language is a complex cognitive ability involving several areas of the brain. The blue area in this image is Broca's area, which is vital for speech production. The green area is Rinkel's area, which is responsible for understanding other speech. The and other areas work in tandem for many types of communication. And we have learned that damage to particular regions within the left hemisphere produces specific kinds of language disorders or aphasias. The portion of the frontal lobe where is called broadcast area, and it is vital for speech production. Further studies of aphasia have greatly increased our knowledge about the neural basis of language. Broca's aphasia is also called non-fluent aphasia because speech production is impaired, but comprehension is mostly intact. Damage to the left frontal lobe can produce non-fluent aphasias, in which speech output is slow and halting, requires great effort, and often lacks complex word or sentence structure. But while their speaking is impaired, non-fluent aphasias still comprehend spoken language, although their understanding of complex sentence can be poor. Shortly after Broca published his findings, the German physicians Rinkel writes about a 59 years old woman he referred to as SA, who had lost her ability to understand speech. Unlike patient with damaged for broadcast area. She can speak fluently, but it doesn't make sense. So she offered absurd answers to questions, used made-up words, and had difficulty naming familiar items. After her death, Rinko determined that she had damage in her left temporal lobe. This caused her difficulty in comprehending speech, but not producing it, a deficit that is now known as wrinkles aphasia or fluent aphasia. Fluent aphasia patients may understand short individual words, and their speech can sound normal in tone and speed, but it is often riddled with errors in sound and word selection and tend to be unintelligible. Another type of aphasia is called pure word deafness, which is caused by damage to the superior temporal lobes in both hemispheres. Patients with this disorder are unable to comprehend heard speech on any level, but they are not deaf. They can hear speech, music, and other sounds, and can detect the tone, emotion, and even the gender of a speaker, but they cannot link the sound of words to their meaning. They can, however, make perfect sense of written language because visual information bypasses the damaged auditorial comprehension area of the temporal lobe. And although Broca and Winkel's work emphasized the role of the left hemisphere in speech and language ability, scientists now know that recognizing speech sounds and individual words actually involves both the left and right temporal lobes. Nonetheless, producing complex speech is strongly dependent on the left hemisphere, including the frontal lobe as well as posterior regions in the temporal lobe. These areas are critical for accessing appropriate appropriate words and speech sounds. Reading and writing require the involvement of additional brain regions, thus controlling vision and movement. Earlier, we mentioned that sensory processing of written words entails connections between the brain's language areas and the areas that process visual perceptions. In the case of reading and writing, many of the same centers involved in speech comprehension and production are still essential. but require input from visual areas that analyze the shapes of letters and words, as well as output to the motor areas that control the head. And one of the important parts in our brain is called executive function. Some of the most complex processes in the brain occur in the frontal cortex, also called PFC, the outer-folded layers of the brain located just behind your forehead. The PFC is one of the last regions of the brain to develop, not reaching full maturity until adulthood. This is one reason why children's brains function quite differently from those of adults. The processing that takes place in this area is known as executive function. Like the chief executive officer of a company, the PFC supervises everything else the brain does, taking in sensory and emotional information and using this information to plan and execute decisions and actions. Specific areas of the PFC support executive functions such as selecting, rehearsing, and monitoring information being retrieved from long-term memory. To serve these functions, the PFC also interacts with a large network of posterior cortical areas that encode specific types of information. For example, visual images, sounds, words, and the spatial location in which events occurred. Although more fully involved in humans, some aspects of executive functions are displayed by other animals. Studies in non-human pyramids have shown that neurons in the PFC keep information active or in mind, while the animal is carrying out a task that depends on it. This is analogous to working memory in humans, which is a form of executive functions. And executive functions can be considered a blend of three core skills: inhibition, working memory, and shifting. Inhibition is the ability to suppress a behavior or action when it is inappropriate, such as calling out loudly when one is in an audience or classroom. Even toddlers demonstrate hints of a developing inhibition ability, as shown in their ability to delay for at least a short period of time, and eating a treat placed in front of them. By the time children reach preschool, they can tackle more complex inhibition tasks such as luscious hide game, and in which they are told to make a fast when shown a finger and a finger when shown a fast. This test, which requires inhibiting their more automatic imitation of adults, is very hard for 3 years olds, but 4 years olds perform significantly better. As people grow older, they wield this ability ever more skillfully. In addition to inhibition, this head game and similar tasks rely on working memory, which is the ability to hold a rule in mind while you decide how to act. When you have new experiences, information initially enters your working memory, a transit from form of declarative or conscious memory. Working memory depends on both the PFC and the parietal lobe. It gives you the ability to maintain and manipulate information over a brief period of time without external aids or cues, such as remembering a phone number without writing it down. Most people can memorize and recite a string of numbers or words over a brief period of time. But if they are distracted or there is a time log of many minutes or hours, they are likely to forget. This shows the duration of working memory, which requires active rehearsal and conscious focus to maintain. The third key component of executive function is shifting, or mental flexibility, which allows you to adjust your ongoing behavior when conditions require it. For example, in the card sorting task, people must figure out that they must switch from sorting by one rule such as suit, and begin sorting by another, such as number. People with damage to their PFC have great difficulty doing this and tend to stick with the first sorting rule. Children's ability to shift successfully between tasks follows a development course through adolescence. It appears that preschool-aged children can handle shifts between simple task sets in a card sorting task, and later handle unexpected shifts between increasingly complex task sets. Both behavioral and physiological measures indicate that the ability to monitor one's errors is evident during adolescence. By mid-adolescence, more complex task switching reaches adult-like levels. Because of its greater need for multiple cognitive processes, mature shifting likely involves a network of activity in many regions of the PFC. And many of the changes in executive functioning ability are gradual. Although the changes are more apparent in young children, the PFC is the main region implicated in executive functioning. However, the skills that fall under this umbrella use input from all over the brain. Interestingly, the activity level associated with executive function actually decreases as children and adolescents mature, reflecting the fact that these circuits become more fine-tuned and efficient as the neural network mature. And about decision making. The fundamental skills of executive function, inhibition, working memory, and shifting, provide the basis for other skills. One of these is decision making, which requires a person to weigh values, understand rules, plan for the future, and make predictions about the outcomes of choices. You make many different types of decisions every day. Some of these rely primarily on logical reasoning. For example, when you compare the timetables for the bus and subway to determine the quickest way to get to a friend's house. Other decisions have emotional consequences at stake, like when the person you are trying to impress offers you a cigarette. Your desire to be accepted may overweight your rational consideration of smoking's harms. This is an example of effective decision making. And both types of decision making involve the brain's prefer- prefrontal cortex. And in particular, activity in the lateral PFC is especially important in overriding emotional responses in decision making. The area's strong connections with brain regions related to motivation and emotion, such as amygdala and nucleus accumbens, seems to exert a sort of top-down control over emotional and impulsive responses. For example, brain imaging studies have found the lateral PFC is more active in people declining a small monetary reward given immediately in favor of receiving a large reward in the future. This is one of the last areas of the brain to mature, usually in persons' late 20s, which explains why teens have trouble regulating emotions and controlling impulses. The orbital frontal cortex, a region of the PFC located just behind the eyes, appears to be important in effective decision making, especially in situations involving reward and punishment. The area has been implicated in addition as well as social behavior. And this picture shows that 7 steps of decision-making process. First, identity the decisions and gather the relative information and identify the alternative and weigh the evidence and finally review the decisions. And that's all for the chapter 5.